HC, the unit circle and the trigonometric ratios. Let's look at what the unit circle is and what its equation is. Here is a circle. We place the center of the circle on the origin of the coordinate system. The center of this circle is 0, 0. What is the radius of the unit circle? The radius is always 1. If the radius is not equal to 1, it's not called a unit circle. So unit circle always has the radius equal to 1. What is the equation of this unit circle? Let's derive the equation of this unit circle. We can pick up any point on the unit circle. Any point to the center, the distance equals the radius r. In this unit circle, the radius is 1. If we draw a perpendicular line from P to the x-axis, this green one represents the y-coordinate, and this one represents the x-coordinate. X, y, and 1, they form a right triangle. In this right triangle, we can have the Pythagorean theorem. So it's x squared plus y squared equals 1. And this one is also the equation of the unit circle. Angle measurement. We have already learned the positive angle and the negative angle in 8a. Let's review the positive angle and the negative angles again. A positive angle means you rotate the terminal arm counterclockwise. Negative angle means you rotate the angle clockwise. But for any angle, we always have 3 elements: initial arm, vertex, and the terminal arm. When we need to talk about the positive and the negative angles in a coordinate system, we need to make sure this angle is placed in standard position. What is an angle in standard position? We always place the initial arm on the positive x-axis, and the vertex of the angle is always on the origin of the coordinate system. And here we place the initial arm. So right now we only need to look at the terminal arm. If I rotate this way, this blue one is a positive angle. If I rotate the terminal arm clockwise, this is a negative angle. Right now, let's sketch the following angles. And make sure when you sketch any angle in the coordinate system, this angle must be placed in the standard position. Let's look at the first one, 65 degrees. Positive angle. So you always place the vertex at the origin, and your initial arm is here. For 65 right now, it means I rotate the terminal arm counterclockwise with 65 degrees. So this is a positive 65 degrees. 120. Place the vertex of this angle at the origin. Initial arm is here. Then I rotate counterclockwise with 120 degrees. This is a positive 120. Likewise, 240. We rotate the terminal arm starting from the positive x-axis with 240 degrees. So this is a positive 240 degrees. 315. We start from here. We rotate counterclockwise 315 degrees. So this is a positive 315 degrees. Negative angles. The only difference between positive angle and the negative angle is the direction of your rotation. Negative 312 degrees. That means you still place the vertex of this angle at the origin, and your initial arm is still placed on the positive x-axis. But for the terminal arm, you rotate clockwise with 300 12 degrees. So this right angle is negative 312 degrees. And make sure you also can use an arc with an arrow to show the direction of your rotation. Likewise, negative 245. I will start from here and rotate clockwise with 245 degrees. So this is negative 245 degrees. Negative 150. Start from here, rotate clockwise with 150 degrees. This is negative 150 degrees. Negative 15 degrees. Start from here, rotate clockwise with 15 degrees. This is negative 15 degrees. Right now, for any angle, we also can use the quadrant to describe in which quadrant the terminal arm terminates. For example, this one I can call quadrant 1 angle, or the first quadrant angle, because this 65 degrees, this terminal arm terminates in the first quadrant. This one can be called quadrant 2 angle, or the second quadrant angle. Quadrant 3 angle, quadrant 4 angle, negative angles are the same. I only look at in which quadrant the terminal arm terminates. So this one terminates in the first quadrant. So I will call quadrant 1 angle, quadrant 2 angle, quadrant 3 angle, quadrant 4 angle. The definition of sine, cosine, tangent, plus 2 important trig identities. There are 2 definitions. The first definition is called the general definition for 3 primary trig ratios. Sine theta equals opposite over hypotenuse. This is what we learned in Math 10. But right now, what is sine theta? We don't call the opposite side anymore. Look at this opposite side. It's the y coordinate of the point on the terminal arm. R represents the distance from this point to the origin. So R is the distance between O and the P. This R equals square root of x squared plus y squared based on the Pythagorean theorem. You can also say this angle theta is contained in a right triangle, but we need to extend SOHCAHTOA to a more general trig ratio definition. So this sine theta we call y over r. Cosine theta is defined as x over r. Tangent theta is defined as y over x. Very similar to SOHCAHTOA that you learned in Math 10. And then remember, this r is the distance between O and P. P is any point on the terminal arm. Based on the Pythagorean theorem, this r equals the square root of x squared plus y squared. So r is always positive. For HR students, we need to introduce the other 3 trig ratios. Y over r is called sine theta. Our early mathematician was thinking, if I flip the ratio, can I give this ratio a trig name? So people find, okay, we can define this one as cosecant theta. It's called cosecant theta. So if I flip this ratio, cosine theta, I flip the ratio to form r over x. This ratio is called secant theta. It's called secant. If I flip this y over x, so this x over y is called cotangent. So this one is called cotangent theta. Based on the first general definition for 6 trig ratios, we can also define the trig ratios in their unit circle. In the unit circle, the radius is 1. So for any point on the unit circle, let's say this is the angle theta. This is the initial arm, this is terminal arm, so it's angle theta. Let's say this point of intersection between the terminal arm of angle theta and the unit circle be x and y. X and y are the coordinates of this point. The distance from this P to the center of the circle, or we can see the origin, is 1. Based on the general definition, we can know sine theta equals y over r, but r equals 1. So we can have y over 1, which is y. Cosine theta equals x over r. R equals 1. It's just x. And the tangent theta equals y over x. For HR students, you can derive the trig ratios in the unit circle based on the general definition yourself. So cosecant theta should be 1 over y. Secant theta should be 1 over x. Cotangent theta should be x over y. This unit circle definition is just a little bit more special than the general definition, in which your r value equals 1. But with this r equals 1, we can rewrite the coordinates of this point P. This P have the coordinates x and y. What is x right now? It's just cosine theta. So this x and y can be rewritten as cosine theta for x. And y is just the sine theta. So right now we also can use the trig ratios, cosine theta, sine theta, to represent this point of intersection between the terminal arm and the unit circle. From the above definition, either of these two definitions, we can also derive two important trig identities. Of course, we will learn more identities in chapter 11. But right now, just by looking at these two definitions, we can derive the first one. Look at this tangent theta. Tangent theta equals y over x. But based on the unit circle definition, this y is the same as sine theta. And this x is just cosine theta. So the first trig identity we can derive from this unit circle definition is tangent theta equals sine theta over cosine theta. X and y and this one, they form a right triangle. Therefore, x squared plus y squared equals 1 squared, which is 1. And this x right now is cosine theta. So cosine theta squared plus sine theta squared equals 1. And this is a representation for cosine theta squared, which is the same as cosine theta bracket squared. This one is sine theta bracket squared. We can ignore the brackets. We can put the square between sine and theta to show a little bit kind of a more concise representation. So sine squared theta is the same as sine theta bracket squared. So cosine squared theta plus sine squared theta equals 1, or sine squared theta plus cosine squared theta equals 1. This is the second important trig identity that we can derive right away from the definition. In section 4, let's investigate the signs of trig ratios. But when we investigate the signs of the trig ratios, we also need to practice the general definition for the trig ratios. Let's look at if the terminal arm passes this point 3, 4. 3, 4 is in the first quadrant. The terminal arm passed through this point. Are you able to use the general definition to find 3 primary trig ratios of this angle theta? HR students also are expected to find the trig ratios for cosecant, secant, and the cotangent, those trig ratios. So sine theta equals y over r. So right now I'm missing the r value. How can we find the r value? R equals the square root of x squared plus y squared. So x coordinate is 3 plus 4 squared. Square root of 25 this is 5. So when the terminal arm of theta passes through 3, 4, sine theta equals 4/5. Cosine theta is x over r, should be 3/5. Tangent theta equals y over x. We should have 4 over 3 here. By applying the same general definition of trig ratios, we can find 3 primary trig ratios for quadrant 2 angle, quadrant 3 angle, and quadrant 4 angle. So right now, let's investigate the signs of those 3 primary trig ratios in each quadrant. In the first quadrant, I can discover all trig ratios are positive. HL students can use the reciprocal feature to find the signs of cosecant, secant, and cotangent yourself. They must be positive in the first quadrant as well. In the second quadrant, or we can say for the second quadrant angle, only sine is positive, and the other two, cosine and the tangent, both of them are negative ratios. For quadrant 3 angle, only tangent is positive, the other two are negative. For quadrant 4 angle, only cosine is positive, and the other two are negative. HL students need to look at how you can use the reciprocal property to derive the signs of cosecant, secant, cotangent in quadrant 2, quadrant 3, quadrant 4 yourself. For example, if sine is positive for a second quadrant angle, then I can know cosecant must be positive as well. Cosine is negative, secant must be negative. Tangent is negative, cotangent must be negative as well. We can summarize the signs of those trig ratios in 4 quadrants into an acronym, which is called OR Students Take Calculus. OR represents all trig ratios are positive in the first quadrant. Students, the first letter S represents only sine is positive in the second quadrant. Take, the first letter is T. T represents tangent. Only tangent is positive in the third quadrant. Calculus, the first letter C, representing cosine. Only cosine is positive in the fourth quadrant. We practiced how to use the general definition of trig ratios to find the trig ratios in section 4. In section 5, we need to look at how to apply the unit circle definition to find the trig ratios of those angles. 0 radian, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. And the unit circle definition is a very good method to derive the trig ratios of those angles. Those angles are a little bit different from the angles in section 4. In section 4, you can see all the angles terminate in the quadrants, but those angles are terminate on the axes. We also call those angles axis angle. If the terminal arm of this angle terminates on the positive x-axis, positive y-axis, negative x-axis, negative y-axis, we call those angles axis angles. Let's look at how we can use the unit circle to find a sine 0, cosine 0, and a tangent 0. Angle 0 is here. The terminal arm coincides with the initial arm. You don't rotate this angle to form 0. So with this unit circle, I can get to the point of intersection between the terminal arm and the unit circle. I can write on the coordinates of this point of intersection very easily. The coordinates are 1 and 0. The corresponding r value is 1. Therefore, sine 0 equals y over r equals 1, y is 0. So it's just y equals 0. And cosine 0 is x, and x value is 1. Tangent 0 is y over x. It's 0 again. Likewise, we also can find the three primary trig ratios for pi over 2. Where's pi over 2? Pi over 2 terminates on the positive y-axis. So right now, we write out the coordinates of this point of intersection between the unit circle and the terminal arm. So the coordinates are 0 and 1. Sine pi over 2 is y, the y value is 1. Cosine pi over 2, x is 0. And y over x, 1 over 0. But what is 1 over 0? For this fraction, we cannot have the denominator equal 0. So 1 over 0, this fraction is called undefined. Undefined, this word has many letters. It's a long spelling. So we will use a symbol. We put on a O or 0, then we put a slash on this O or 0. So it's called undefined. This symbol is also called null set in the set theory. Right now, let's find the trig ratios of angle pi. So pi terminates here. This point should have the coordinates -1, 0. R equals 1. So sine pi is 0. Cosine pi is -1. Tangent pi is 0 over -1, which is 0 again. 3 pi over 2. This angle terminates on the negative y-axis, 3 pi over 2. The corresponding coordinates of this point should be 0, -1. So sine 3 pi over 2 is -1. Cosine 3 pi over 2 is 0. Tangent 3 pi over 2 is -1 over 0, which is undefined again. Let's look at the last one, 2 pi. 2 pi, you start from here and then rotate one full rotation, and this 2 pi still terminates on the positive x-axis. And we also call this 2 pi is coterminal with this angle 0. If you have two angles which are coterminal with each other, they must have the same trig ratios. Let's use this one to justify. So let's look at the coordinates of this point. Should be 1, 0 again. R equals 1. So sine 2 pi is 0. Cosine 2 pi is 1. Tangent 2 pi is 0 over 1. Those three trig ratios are exactly the same as those three trig ratios. Right now, let's look at section 6, periodicity of trig ratios. The periodicity of trig ratios also can be called two coterminal angles must have the same trig ratio values. For theta in radians and k is an integer, theta also can be in degrees. We still do have the same periodicity of trig ratios. Sine theta plus 2k pi. What is sine theta plus 2k pi? K can be any integer. Let's assume theta is in the second quadrant. So if theta is here, if k equals 0, theta plus 0 is just theta itself. But like if k is 1, theta plus 2 pi. Theta plus 2 pi is the green angle compared to the blue angle. So theta plus 2 pi, you just rotate one more rotation, then theta. And theta plus 2 pi and theta, they terminate in the same position. Look at the purple angle. It's theta plus 4 pi. Theta plus 4 pi, in comparison with the theta blue angle, you just rotate two more rotations, then theta. All those angles can terminate in the same terminal arm. If those angles have the same terminal arm, you can get the same coordinates on the terminal arm, and then the R value must be the same as well. That means the sine ratio must be the same. So theta plus 2k pi is always coterminal with theta. For two angles which are coterminal with each other, they must have the same trig ratios. Therefore, sine theta plus 2k pi is the same as sine theta. Likewise, I also can derive cosine theta plus 2k pi equals cosine theta, because theta plus 2k pi is coterminal with the theta. Tangent theta plus 2k pi equals tangent theta. Periodicity of trig ratios is one pattern rule for trig ratios. We do have more than this pattern rule in the trig ratios. We are not asking you to prove those pattern rules mathematically. However, we are expecting you to use concrete examples to derive those pattern rules. Let's look at section 7 and section 8. Try to use the graphing calculator to help you find the following trig ratios and summarize the pattern rules you can discover from those questions. Let's look at section 7. Use your scientific calculator to find the following trig ratios and summarize a pattern rule. Sine 20. Let's look at sine 20. Since 20 is in degree, we need to shift our mode on the graphing calculator from radian to degrees. Let's press enter and quit. So sine 20 degrees is 0.342. Let's look at sine 160. Sine 160 degrees, 0.342, it's exactly the same as sine 20. Therefore, we can see sine 20 equals sine 160 degrees. Likewise, you also can use your scientific calculator to get cosine 37 degrees. If we just keep three sigma figures, it's 0.799, and cosine 143 degrees is negative 0.799. Tangent 55 degrees is 1.43, and tangent 125 degrees is negative 1.43. Feel free to illustrate more examples to see if the pattern rule you can summarize is correct. The first one, I can observe these two angles. The relationship between these two angles is they add up to 180. Therefore, the first pattern rule for these two trig ratios, I can say sine theta equals sine 180 degrees minus theta. If we change to the radian measures, it should be sine theta, theta in radians equals sine pi minus theta in radians. Let's look at what a pattern rule can we discover from the second example. If these two angles are supplementary, the cosine ratios are opposite to each other. So I can summarize as cosine theta equals negative cosine 180 degrees minus theta. In radians, it's cosine theta equals negative cosine pi minus theta in radians. The same can be applied for the last example. These two angles are supplementary and their tangent ratios are opposite to each other. Therefore, tangent theta equals negative tangent 180 degrees minus theta. Or in radians, it's tangent theta equals negative tangent pi minus theta. Section 8. We still need to use the graphing calculator to find the following trig ratios and discover the pattern rule from each example. We change the angle measures to radians. So if I want to use the calculator, make sure you shift the mode from degrees back to radians. So let's quit. So sine pi divided by 6 equals 0.5. Sine negative pi over 6, it's negative 0.5. If two angles are opposite to each other, their sine ratios are opposite to each other as well. So from the first example, I can derive sine negative theta equals negative sine theta. We also can observe this example and discover the relationship between these two cosine ratios. Cosine 3 pi over 4 is negative 0.707. Cosine negative 3 pi over 4. We can see these two ratios are the same. Therefore, I can derive cosine negative theta equals cosine theta. Use the calculator to discover the relationship between these two. Tangent 1.18 is 2.43. Tangent negative 1.18 is negative 2.43. Therefore, tangent negative theta is negative tangent theta, just like the sine. SL students are not required to really understand those pattern rules, but HL students, you are encouraged to develop your knowing and understanding on those pattern rules and get familiar with all those pattern rules for further learning. Here are the homework questions. This is the end of the lesson.